Hello. Works. Okay. So in terms of logistics, that was just about the project and some sign up that you need to do. Um, we will. So now let's discuss assignment 3 because that was the deadline was yesterday. We'll briefly discuss that and then get into then I'll talk about lecture goals. Okay, let me not cover everything now. So let's talk about assignment 3. I know there was an issue with versioning, and this is exactly the types of issues you'll face in many Python-based projects, and that's why there's this whole idea of virtual environments, or even whether it's Conda-based or whether it's virtual or VN-based. There's tools like Python Poetry. I don't know if anybody has used something called Poetry. It's also a way to kind of control what versions you work on and what other people in your team or somebody 2 years later should work on. Everything is documented nicely. Okay, so anyway, here unfortunately this repository they don't have. They do mention, I think, versions, but it's not like in a satisfactory manner. It's not like you can just pip install -r requirements and then everything is nicely working. That's not the case. So we have. Yeah, so I just shared another notebook there for question 1. So I don't know if everybody was everybody able to at least attempt question 1. Okay, so I don't know if you used example starter notebook that I gave or not, but let me briefly discuss the notebook that I gave. It's already using LSTM, so you don't really have to change anything. I think the previous older script was using RNN, and you had just changed it to LSTM, at least for that part. Okay. The big change is actually changing the model definition, right? So here you will actually see that they're doing. So the notebook that I shared is from a reference blog post here. And what they are trying to show is actually all the details of how to massage your text. Okay, text data is not numeric; it's already not in an x, y type of format that you would see in scikit-learn. So they're showing how the data looks like. It's basically a list of lists, and you can do some splitting. But the most important step is basically coarsely. One step is tokenization. The second step is actually feeding the data as a batch, which means the right shape and size into the model. Okay, so those are 2 steps. Let's say tokenization is just you don't have to do all these extra. You don't have to always do it, and it's good to do it if you want to kind of not recognize a capitalized capital case word as a different from a lowercase word. If you want to say they're the same, then you can actually do these types of operations. Okay, you can for example, text.lower will lowercase everything so that it's the same word. I mean, there could be false issues here also. Like New York, if you the new word, if you lowercase it, then it you wouldn't you would lose some meaning there. So anyway, this function is just making the splitting the text into a collection of into a list basically. Okay. And then you're trying to figure out, okay, if I can apply this function on all my data in my training data, for example. You could also do just instead of just train data, you can do both train data and validation data. That way you don't have. I mean, that way at least you don't have missing words, but the vector embeddings for those words will not be trained unless obviously you get vector embeddings from elsewhere. In the sense that even if you include those words in your vocabulary, which are only in the validation and not in train, it's unclear like how much it's not going to be useful because when you're using training data only, those words and their embeddings are never going to be touched. Okay, so anyway, the decision here is just what the decision they have done is just use training data, tokenize all of them, and just kind of accumulate them. Okay, this step dot update is just think of it as essentially some sort of dictionary, and you're it's not exactly a dictionary. It's also keeping track of counts of those things, but you're just collecting all those tokens together so that in that sense you can get a sense of the vocabulary size. Okay, so literally the size of this counter token counts is going to give you the vocabulary size. Okay, torch text makes it easy to get that easily by creating a basically wrapper function, wrapper, I guess. Yeah, let's call it function, but just creates a vocabulary object from which you can say, okay, what's the size of vocabulary, what's the index of a word in my vocabulary, and so on. Okay, but you could do it manually as well. So which is what it's mostly here we are sorting the items according to their counts, and then we're creating an order dictionary, and then we're passing the dictionary into this vocab function. Okay, you don't have to use a vocab function or torch text here. You can just work with it yourself. Okay? And they also insert, and this is where I think extra information is needed, right? So this is not something you would do in image or tabular data, but here you want to take into account that, and this is something that requires knowing that later on you need kind of a batch of text for which you're gonna do forward passes. So for that you need to pad, because all text is not equal length, different sequence lengths. And also to deal with missing words, okay, words that you've not seen. So here, so those two extra tokens are added here. And this object makes it easy to add those tokens and give them a special, I guess, index. But you could have just included that in your like a dummy sentence or dummy token that you can tokenize and just get some indices for that. Okay. And it's just for example, if these are the words, what would the index of those words be? Is something that's printed here. The next is simple functions. So lambda functions are just inline functions that you can define in Python. So just a Python feature. You don't have to write lambda functions. You could write explicit functions here. So all functions is just going from index to it's basically for every, so it's a function which is taking a word as an input and producing the it's taking a sentence as an input, and for every so an tokenizer of X will give you each word of that sentence, and then for each word or token in the sentence, get the index of that word. So it's all captured in this. This is called a list comprehension. Again, a Python feature. You could just write for loops here, but something you wanna, if you're new to Python. Otherwise, you would have seen this before. Okay. Same thing. You just, again, a lambda function just says, okay, in the data, if data has, I think, 1 and 2 for this particular task, which is sentiment classification. We are not doing sentiment classification in our assignment. We are doing language modeling. But for sentiment classification, you could have, they needed this. Okay. So we don't have this. Okay, and we have to actually work with input data itself and try to use the 0 to n-1 indices to predict the first to n index. Okay, so that's the new part. That's something that you need to add. This is just shifting data and shifting data to the GPU if you have. And this is where I think there's this function where we are doing several steps. So we are applying those above functions, label pipeline and text pipeline, to create our tensors. Okay, so this collate just means, like, I guess, process a batch of data so that it's in the form which is consumable by the model in the forward pass. Okay, so for that, basically, first, obviously, your input data is a sentence, which is a collection of words or tokens, and you have a label. First, you need to convert them into, you want to get a batch and then convert them into tensors, right? And this is where first you get the indices. So first of all, you get rid of all the characters or whatever words. So here you're getting those indices, and then you're actually calling pad sequence to pad zeros to those sentences which have less number of words. Okay, so this is something you would have seen. It's needed even for this classification task, but it's also needed for your language modeling task. Okay, so that's why. So we are going through these steps because this is some extra things that you need to take into account because of you're working with text. Okay, so what's happening, right? So iterate over all batches, all I guess items in a batch. So in a batch, you would have, let's say, 5 sentences. Let's say the batch size is 5. Then each sentence you're basically you're figuring out what is its label. If you need to transform it instead of 1 and 2, you want to transform it to 0 and 1 or something, you're doing that. And then you're creating that list of so you're creating a tensor out of these indices, okay, for that sentence. And then you're appending that to a list. Okay, that's all. So you're basically collecting a list of these tensors, but they're not of the same length, and you need to make it of the same length. Okay, that's where so first of all, you're looking at what is the yeah. So labels are fine. Labels are easy to process. Okay, and this is the length of all the sentences. And now you're actually padding by calling this pad sequence function to this list of tensors, so that you can get the same length. Okay, and then there's an extra function called pack pad sequences to kind of make it more efficient. For that's behind the scenes detail, but it's something that you can call to make the representation more efficient. Okay, instead of having tons of zeros, tons of I guess padded indices, you could have a more compact representation of the same batch. Batch is like, think of five is the batch size, and sentence, let's say, is max 20. Then the 5x20 matrix or tensor with all these token indices may have a lot of zeros. Instead of explicitly representing them, you could compress that. Okay, so that's a more, it's nothing data sciencey here or anything model related. It's just trying to compress the representation. Okay, and batch first is again, if you recall, for RNNs also, you could, when instantiate RNNs, you could use this batch first to kind of, if you know that your tensor that's going through the forward pass actually has the first index representing the batch rather than the second index. Okay. Yeah. Any questions here? I mean, so this is something that you would have already done, but we're just recapping slowly again, so that you remember that for text, there's some initial bunch of steps that, these are like helper functions. They'll be same functions irrespective of whether you're doing translation or classification or something else, language modeling. So if you write them once and have these helper functions, you can just copy paste them everywhere else. Okay. Yeah, and that's pretty much, that's the heavy lifting. And once you have that, you can define your data loaders, and that's where this function that you created above called collate is what is passed as an input to this data loader object that you're creating. Okay, so this is how you custom design your, like, if you need to process your batch of data, which is not in the format that the model is expecting, you want to have that extra function. Okay. You could always have the function and just have it as like a dummy function, and just, whatever x comma y you get, you just return x comma y if you want. But it gives you a sense of like, how do you, if you need to throw away some coordinates, like maybe the raw data xy has an extra feature that you don't care about, you can just index it by saying, okay, 1 colon, and drop the first feature, for example, first feature coordinate. So things like that you can do using this collate function. I mean, that you need to write. If you don't write it, then when you pass data, you'll have to do extra processing outside your model function call. Okay, so either you put it in the collate batch function here, or you could do, you could have a bunch of lines right before this where you do all that processing, but it look pretty messy, and so that's why it's captured in that collate function, so that when you get the data. When you get the data from get a batch of data from the data loader, you are actually getting the processed 3 tuple instead of the sentence and the label. Okay, the original dataset object, our original dataset basically just has this dataset just has the sentence itself in English or whatever, and the label, right? So you've already processed that nicely into tensors that can just be passed to the model, okay, easily. So that's what's going on here. So this is for classification. So there are a lot of changes that you need to do for your language modeling task. Okay, and there are many ways to do it. An inefficient way is to say, okay, I'm not gonna worry about doing simultaneously the modeling for second word to the last word. I can create like an expand out saying, given 2 words, I'll predict the third word. Given 3 words, I'll predict the 4th word separately. So you would have like a huge blow up in terms of input outputs. But that's still okay. I mean, it's inefficient, but in terms of modeling, it's still okay to do that. And then you would still be in some sense, basically in the same. You will have the same script, except the model definition would change. So here, this the output size would be the vocab size that you it's the same vocab size as the input size actually. So you would have the same dimension. Okay. If you do that, then now you're predicting, given an arbitrary length input of words, which we just saw the processing for, you're predicting a word out of your vocabulary. Okay. So this step here, self-code embedding, is an instantiation of that going from a token to a vector. Okay, and we'll see that again actually in our slides. Going to token to a vector is where you would have instantiated or used glow or word2vec or anything else like fast text or something in your assignment second question. But this is where you would insert or load that data. Okay, so embedding is, if you actually look at it, it's obviously a nice wrapper class from which you can create an object, but behind the scenes it's just wrapping a tensor, and the tensor is literally every index as a vector. Okay, so basically a matrix. Okay, and so that matrix needs how many rows, how many columns. So if you're using 100-dimensional globe embeddings, then this will be 100, for example, right? And then you have an LSTM. Again, this batch first, in case if you are kind of if you prefer having the batch coordinate to the first index, and then this you're going from there to a linear transformation, and then through a ReLU. Here they're doing 2 levels and then creating a one prediction. Okay, because they're doing binary classification, but we don't have to have this. Okay, so this also has to change. But if you run this and get a feel for how this whole script is running, then you know how to change part by part. Okay. Yeah. So I hope you guys were able to run this, and once you're familiar with like how the text was processed to get it to be input to the model, then you know how to do a language model. Okay. Inefficiently, obviously, for efficiency, you need to play with padding and collate function to kind of create your x and the shifted version of x as x comma y's. Okay, instead of x comma y, where the y is the label here, in your collate function you will have to do x and some shifted version of x as the y. Okay. Any questions about this question 1? Was it too complicated, or this is the peak, right? This is the hardest assignment, I assume, compared to the previous assignment, because previous assignment was about fine-tuning and fixed feature extraction from any CNN, and we used ResNet 18 or something like that. We also did the movie kind of embeddings, but that was more about, it's not a complex model there or anything. It was just trying to process data, which is also something which is new here, to process the text data. So if you have gone through this, then I think this is like the peak. You're kind of ready for all sorts of complex models, or any other model will probably not be more complex. Or at least the model script would be similar. They would just place some things here and there for efficiency reasons or other things. Okay. Any questions? Yeah.
In the R and like the class.
Yeah. Yeah.
I didn't think about this question before, but where does it use the previous, like where can you see that it's using the previous input and then hit?
Yeah, so that is completely captured in this so this LSTM is not there's a difference between LSTM and LSTM cell or RNN and RNN cell. RNN cell would be the one which would explicitly just take the previous inputs and produce just the hidden vector. So you would have to do a for loop if you use RNN cell here. But we're calling LSTM, so it knows given the given its input, given the batch, given the so whatever is the length of the input, it knows how many times it has to iterate and do the same computation how many times. Okay, so it's not that it knows, it just whatever the input, it just has to do that many times. Okay, so so you can see that that's why you are okay. So in the forward pass, this is the efficiency thing, which is just behind the scenes, as I said. Once you add the paddings, you can make it more efficient by not representing zeros again and again and again, or whatever the padding tokens again and again. But when you called self.rnn, you would have gotten you would have gotten all the hidden vectors, and then you're only picking essentially like the last one. I mean, yeah. So now I'm gonna say, okay, what are these indices and so on. So this is where I think accounting for your coordinates makes sense. You need to see. So this is an LSTM. What would be its output? Like I think last time we saw in the PyTorch documentation, or 2 times ago, we saw like what was each of the coordinates, and so we need to check what each of the coordinates is and how we are splitting that out into, let's say, these 3 tuples, and then pick the. So in their case, they're doing classification. They only need the last hidden vector, for which they need to just transform and make the prediction. But if you are doing that more efficient version of language modeling, then on the training side, you would reuse all the hidden vectors. Okay, so because you would get, for the first word, you would get the while you're decoding, there's no decoding here at all. But when you're decoding, you can actually get the first cross entropy loss with just the first prediction, and so all the hidden vectors help. Okay, you don't have to discard them. Here we're discarding all the hidden vectors. I mentioned decoding, but that's I think I myself got confused with the second question, which is about translation. But for here, you could actually, so it would still be a regular RNN. It's just that for every hidden vector, you can map it to the next word that you need to predict. So there's no need to decode, but you can compute multiple cross entropy losses together instead of like separately doing it. But yeah, this is doing a for loop, if that's your question. Yeah, there's some extra arguments here, like what is the length, and so if you don't do this packing, then you just need to double check that it should work still. It's going to be very inefficient. Okay, so you can check the RNN definition. It doesn't expect a packed. I think it doesn't expect a packed version of the tensor. Like basically, packed just means get rid of 0 representations, basically. At least in this script, I think you can always go back to this blog post, which actually has the sample outputs. I didn't use the sample outputs here, but look at the blog post. They show all some example outputs of what packing means and what how are you efficient and stuff. Okay. Any questions on the first question? So it's just Marco is probably easy. You just have to count and normalize how many times given the previous word, or whatever is the n-gram here. But whatever is given the previous few words, how many times did this third word or fourth word occurred? Yeah, and then you just have to report some report some outputs. Yeah. Any questions for this? Okay, everybody's like, okay, this is too easy. Because this is actually the question where I think if you spend time, this is what's going to give you some dividends later on. If you want to work with text, this pretty much shows everything that's happening in a typical text workflow. Okay. Yeah, and the next question is, again, you have very small data set here, so it's the quality of output is not expected to be high at all. But you are just learning how to do an encoding and decoding type of a model. Okay, so remember the model, canonical model is just the RNN block basically, or just the RNN cell, which we discussed as RNNs and then LSTMs and GRU cells, whatever. They can be connected, basically like assembling a Lego. They can be used to do sentiment classification. That was the example script that we have. Or it can be used to do translation. And to do translation, you kind of think of, oh, there's an encoding phase and there's a decoding phase, and we'll just connect, how they're connected. And therefore, we can bring in attention, for example, encode decode attention. How we're going to decode, for example, using beam search heuristic to kind of take care of errors in the initial decoding, for example. So there's extra things that happen if you want to do translation, which is a variable length input and a variable length output, where the variable length output comes after the variable length input is completely processed. Okay. Whereas in language modeling, the variable length input and variable length output, but the variable length output starts immediately, essentially immediately right after as the variable length input is being consumed. Okay. So I'll not discuss too much, but except that here for the second language, you would not, Glo would not have the embeddings for it, right? So you would have to either you say, oh, okay, I'm not going to use any embeddings, and or I'm not going to use any pre-trained embeddings. So you could still have an embeddings embedding that whose parameters you would learn from scratch. Okay. So in one direction, from English to one language, you can use Glo. So embedding, you have to just use the pre-trained weights. You can load them because they're just a tensor. They're just basically a matrix. Yep, you can load them. But for the second language to English, you don't have the embeddings, so you don't need to load anything, but you will have to learn them when you do that translation. Okay, when you build your translator. So I think there is So Glo, I hope you were able to work with Glo. This is actually, it has its own interesting analysis that you could do, and I think this is where we saw this type of directions and I guess vector directions, vector differences, how they look like. And if you wanted to use the pre-trained embeddings for the second language, you can use something called fast text, which I think it has word vectors for other languages. Okay, so if you wanted to have embeddings for both your second language and your first language, then you could just use you could use this to get your pre-trained embedding, so that it reduces the amount of effort you need, in the sense that you can work with smaller data set basically instead of working with a much bigger data set. So the quality of your translations would probably not be good unless you got really good translation quality. That would be surprising, but if you did, then you might have, I don't know if you just restricted yourself to that data set, that link that was shared, or if you use more data. You need a lot of data to train these. Even this simple no stacking, single decoder and single encoder level model. That was the scope of this question. Any comments? Okay, so what we saw is the assignment 3, which is the last assignment. So that's great. You finished the assignment component. But your project is the next big thing, and this is where I think you need to think of what's your domain of interest and what you want to kind of work on. It could be just embeddings, it could be visualizing embeddings, it could be image embeddings, text embeddings. For example, just based on what we discussed now, it could be the translation type of model, but or it could be auto reply and stuff like that we saw in the class. It could be image captioning. It could be the opposite of that, but opposite of that we've not studied. Okay, which is to go from text to image. So you could pick any of these, for example, and this is not the only scope. I mean, you can pick anything you want. Today we'll actually go through an example of using pre-trained models, in particular transformer models, to use instead of these fixed embeddings. We'll use contextual embeddings, okay? Contextual word embeddings. Okay, so that's a new thing. Yeah, I don't have much to say about the projects here, but any questions about how all this is connected? Okay. So that I just wanted to briefly discuss the assignment questions. I didn't go into the details of the second question, but I mean, I think it's at least in terms of description, it's straightforward. Obviously, there's a lot of challenges in getting this to work. But as I said, we saw the pre-processing gory details for just classification, right? So same type of effort goes into any other type of model here, okay? And it doesn't even, it's not restricted to even just RNN models. It, even if you have transformer models, you have to do that tokenization here. You have to kind of get to that representation where you map from token indices to some encoder, some embeddings, okay? Okay, so what we'll do today is actually come back to our slides, and last time we introduced the transformer architecture, which means we discussed about what's self-attention, what is these keys, queries, and values, and how is that how is it defined at one unit level of an encoder or a decoder. Decoder actually we did not spend time on, but on the encoder side we realized, okay, there's there's a self-attention sublayer and there's a feed-forward sublayer, and there's also skip connections and all sorts of complexities. So that's where we just went through a forward pass of how does the transformers encoder unit look like. Today we'll just kind of revisit some more ideas about transformers, just extra kind of reinforcing ideas. A little bit older, actually, we're going to look at ideas up to 2018, 2019. And basically, we'll spend a little bit more time on a model called BERT. Okay, so BERT. The T stands for transformer, and we'll look at, and in fact, GPT also the T stands for transformer. We'll look at BERT a little bit more. Okay, and after that, we'll look at if we have time, we'll talk about unsupervised deep learning. We'll just get started today, and the plan is to kind of this one and the next idea we'll talk about in the next couple of lectures, up to the next lecture. Okay, so let me not introduce that now. Okay, so what's the agenda now is what we did last time was up to the second bullet point, which is transformer architecture and the idea of self-attention. Today we'll kind of continue from there. We'll actually kind of again go back to basics actually, and go through one full example of how to do transfer learning using a pre-trained NLP model. And in fact, in our case, the pre-trained NLP model would be a pre-trained transformer based model. Okay. This is basically just kind of analogous to how we first dealt with CNNs, and then we talked about how to use a pre-trained CNN. That was easy relatively. I mean, we just had to fine tune our feature extract. Here, in fact, we'll do the same. We're just going to do essentially some sort of feature extraction. Okay, as in basically we'll get embeddings of words, and then we'll have a little bit of brief discussion about BERT and some related architectures, but mostly a little bit more details about BERT. Okay. So BERT stands, so we'll actually do the example first, and then we'll look at what is a little bit more details about BERT. So BERT is actually, as the title suggests, that's the full name for this acronym, bidirectional encoder representations from transformers. So what are we trying to do here? Because we want to look at what is the use here. Is that previously we've seen word2vec, GLOW, fast text, anything like this for getting ready-made embeddings of words. which is actually already a big delta. I mean, if you just had, if you did not have these embeddings, and if you wanted to process textual data, you could have done something like TF-IDF and all that. But the big delta was already like capturing these semantically similar words having similar vectors. Okay, and already it gives you, if you just do nearest neighbors there, you can actually get a lot already. Okay, so that was a big delta, and from there, the next idea is to use contextual embeddings. Okay? So these embeddings are generated using these transformer-based pre-trained models. So pre-trained models, these are trained from huge amount of corpora, different types of corpora. Sorry, and then you can get embeddings of words. Okay. So let's just see how to use it first as essentially like a black box, and then we'll talk about some details. Okay. Recall that when we're doing the previous sections, we were talking about a specific application, which was translation. Okay, we don't need, so the most important thing, although we're talking about translation, is the definition of that encoder unit. If you're not doing translation, for example, if you're just doing like sentiment classification, like the code that we saw, we don't need the whole decoder thing because there's nothing sequentially that we're doing. So the output is a fixed length, like a prediction of positive versus negative, right? So don't get wedded to that encoder decoder like 2-block architecture here. That only makes sense for translation or variable length input, variable length output situations. So let's look at a model called DistilBERT. DistilBERT is just a really small kind of ResNet 18 instead of the ResNet 50 or ResNet 34 type of model. So it's a smaller transformer architecture. Why are we discussing this is because BERT has, at least Google has reported, Google has reported like using it for search, as not just search and other, many other products within it. And so we want to kind of get a sense of it. In fact, let me show that. So that BERT has its own, I guess, page. So beyond, obviously, it's the best paper award at the top NLP conference. So I guess this is the key information. So it started using BERT for English language search queries, and then it adopted it for search in 70+ languages, and then basically all English queries are being processed by a BERT-like model. So transformers are have become mainstream at least in some large companies, a couple of years ago. So that's why I guess we are just discussing BERT. But BERT is not the only model, as you know. Like today, 2023, I would be talking about BARD or Claude or GPT-4 and stuff like that. Right. So we'll look at how to use this pre-trained model for a specific task, which is, we'll keep the same theme. We'll look at a review classification, a movie review classification type of task, which is the example code that we have anyway. So just to kind of recap again, like really this is low-level detail is what you want to do is given a sequence, given a collection of words in a particular sequence, you want to say whether it's positive or negative. And so if the data, this is how you would, if you just do a save the data, right? So it would, let's say if it's a pandas data frame, one column would be just a string like this, and the other column would be like integer column like this, right? And what you want to do is we want to use this as a pre-trained model, and we've seen how to do this with vision as well, right? So we just have to bring that block in, which will take the sentence and produce potentially an embedding of the sentence. And once you get an embedding, you just call any, you can do just a linear transformation, logic regression. We know it's just a simple neural network as well, or you can just use any other model. Okay, and we'll actually look at the version where we're just doing fixed feature extraction, so you don't even have to have PyTorch-based code. It's just a black box, which is just extracting a vector for a sentence. Okay, so it turns out the DistilBERT, and we'll look at the architecture in a little bit more detail, is that if you give this data frame, pandas data frame, as input to this pre-trained model, for every sentence, you can get this particular model produces a 768 dimensional vector. That we'll talk about. There's nothing specific about it why it's 768. They just chose that as the dimension for BERT pre-trained models. Basically, you get a vector. So for the sentence. Okay, so how do you get that? So generally, what you do is, given a sentence, you would actually have some tokens, just like the unknown and padding tokens that we created in the classification example. Here there will be extra tokens when we train this model. Okay, and that extra token is called a CLS token. A CLS just stands for classification. So we just add that extra token before your sentence, and then do whatever, like pass it through a transformer type of model, transformer based model. Sorry, it's not going to be that encoder decoder thing. Just think of it as an encoder side, in fact. Okay, that means for every word in my sentence, including the CLS token, the first word, second word, and every other word, I would get an embedding. After, remember that on the encoding side, I would get a vector or keys and queries if you want, but basically a vector for every token, right? I'll just focus on the first token, which is the token for, focus on the first embedding or the first vector corresponding to the CLS token, and I'll just use that as my sentence token. Okay, that's what it is doing, and it turns out that the vector corresponding to the CLS token, which is the sentence vector, has enough information, kind of separates, has enough information so that you can actually separate out the positive class from the negative class. Okay, so let's look at the detail. First, you kind of split the data, right? So that is nothing interesting, and okay, I mean, if you already had the embeddings, then you would split the data and do test train and all that. Let me skip that. So let's actually look at the the previous slides were just talking about if you already had embeddings, you would just keep the data and train on one side and then evaluate on the other side. Okay, with any model. So let's actually come back to this BERT pre-trained model. So what are we trying to do is that we tokenize, just like we did in the previous assignment 3. I guess both questions needed tokenization. We just tokenize. It's just that this tokenizer is also is also available. I mean, we actually need the tokenizer because BERT is a pre-trained model, so it has its own version of what word has what index, right? So and also that tokenizer, if it sees an out of vocabulary word, it has to assign it to a specific index as well, right? So that's already predefined. Just like, so you get both the model and the tokenizer with it, so that you know what maps what inside that embeddings that are present in the pre-trained model. So so if you had a vector like this, this vector here. First of all, the word token kind of is used instead of a word because tokens are a little bit more generic than words. So they could be parts of words instead of the full word. Okay, and so here you can see you start with an actual sentence here. You tokenize, which basically is this whole dashed box here, where you basically break it into parts. So this word rumination was broken into 2 tokens here. And then you add some extra tokens. Okay, these tokens are specific to BERT, and they help you use the BERT model for example, classification. So here's the tokenization, very similar to what we did in assignment 3. CLS has sub number 101. Okay, so the function call looks similar to other tokenizers or even what you have used. So just .encode or something, and add special tokens is equal to true is for that tokenizer. Okay, tokenizer for BERT. Any questions here? Yeah. Why is it broken into 2 parts? Yeah, they could also be broken. Yes. So here they have broken it. So they, as in like the people who pre-trained the BERT or BERT model, they gave a tokenizer which is breaking up words into smaller parts. Yeah, for example, GPT-3 or 3.5, their tokenizers will also do something like this. What is the right unit at which you need to represent a collection of characters? Doesn't have to be at the level of a word. Okay, it could be at the level of a subword also. and there are some choices that different groups have made, like OpenAI's ways of tokenizing is a little bit different from maybe the way BERT is doing, and so on. Yeah. No, I mean, this is just a press release from 2019 or 2020, right, on Wikipedia. So I don't know if they're still using it. Yeah, yeah. It doesn't have to. So even if it's when you say multi-line, you're talking about multiple sentences, right? Yeah. So there could be like three sentences, one after the other here. You can use it as long as the pre-trained model can process all of it at the same time. Okay. Even in the sense that you will see that DistilBERT has a limit. I don't remember the limit, but BERT, for example, has a limit of 512 tokens. Okay, that's a lot of words. It's like almost a paragraph. But yeah, so there is some. You can have multiple sentences. Yeah. So here, whatever, like we have some number of tokens, right? 4 plus 4, 9 tokens here, but yeah, whatever the number of tokens, that there is a max limit to the pre-trained model. Even if there is a limit, you could do like some heuristics, right? If you had a longer collection of tokens, you could just pass part of it and then part of it and then try to concatenate, or not concatenate, but somehow some sort of like merge the outputs, fuse the outputs. So once you've tokenized, and then it's very similar to what we did in the example script also that I shared. You just pass it through BERT model. So the model is expecting basically tokenized input. So this is, we are talking about only there's no training, there's no batching. We're just sending a tensor with just like 1 cross whatever is the token, what is the sentence length. Okay. And remember, so we're going to talk about BERT in a model, but it turns out that it's not going to be the encode decode architecture, because we're not doing translation. It's just going to be this pre-trained model is actually just essentially collection of transformer encoder units. Okay, and we'll talk about it in a second. But basically, just on the left side of the picture that we had in the previous application from last lecture, we'll talk about how many stacks, how many encoder units there were, and all that in a second. But basically, you get one embedding or one vector per token. Okay. For translation, we did, instead of one vector, we broke it again into keys and queries. But here we don't have to do that. Okay. We basically get one vector per token. And what is the vector length? It turns out for this model, just happens to be 768 dimensional in length. 768 is some embedding dimension. Just think of it that way. And recall that when you're doing this, each vector somehow is influenced by everything else, right? That's the whole point of self-attention, right? So when you create, when it's producing this vector here, it is kind of attending to every other word that was there in this input. Okay. And yeah, positional embedding and stuff is also happening. Okay, so there's details that are not captured here. Yeah, and it turns out, for this model, the first token, the classification token or the CLS special token, whatever is the embedding for that is quite suitable for doing downstream use of that. So you can actually just think of that embedding as some sort of fixed vector sentence representation. Okay, fixed length vector representation of a sentence. The sentence could be one sentence, it could be 3 sentences, but you have a fixed length representation of that sentence or that input. Okay. I mean, it just happens that if you want to use it this way for classification for downstream tasks, and you want to get representation for all the words, something that represents the sentence itself, then you can use the first token. Obviously, if you just want the embedding for each word separately, then you can just use each of the words embedding if you want to. Okay, that's also fine. Then you don't need to use CLS, perhaps. Yeah. So and then once you have the embedding, you know how to kind of do a forward pass into a logic regression model, which is just a WX plus B type of model, and get a classification output. Right? Yeah, and the rest of it is standard cross validation and all that. So far, by the way, we have not talked about cross validation or anything like that in the whenever we're introducing different types of models, CNNs, RNNs, word embeddings, and all that. Is because it's hard to do that. You don't want to kind of retrain again and again. So folks don't really do cross validation here. Okay, but if you're just doing using pre-trained models and just adapting it to your application, you should probably do these things. Okay, and code for this is actually right here, right? So this is actually using the transformers library, which I'll briefly show in a second. But basically, we are in the transformers library. There's dot model name, so you can get just the dot model name, and then dot model name tokenizer for that model type, and then you're just passing what, and the model turns out also has there's multiple versions of this model. For base uncased means one version which has basically uncased I guess strings. So you just instantiate the model class appropriately with the string, and from tokenizer class you create a tokenizer, and that's it. Okay. When you instantiate the model, you just want to know which pre-trained weights you want. This is the type of pre-trained weights we want for this. Okay. You don't have to have exactly this. You can use other choices of pre-trained weights. Okay. And so yeah, we just instantiate the tokenizer in the model from pre-trained of which type. Pre-trained is just a string here, by the way, just to show it. This is just a 3-tuple assignment to a 3-tuple. That's it in this sentence here. And then we are creating those two tokenizers in the model, and read the data. In this case, we're just getting some data from some location. So we just have a context data frame, right? And then we can just apply again the lambda function, the inline function that we saw earlier. So given x, which is a sentence, we are doing a df 0th column, which is the column with the sentences. We are doing a element-wise application. So dot apply function for when we do element-wise application of function. The function is just taking the sentence, and tokenizer.encode is being called on that sentence. Okay, and we need to add the special tokens because we want the representation for the CLS token. Okay. And so the output of tokenize is just these variable length lists. Okay. All of them start with the 101, which is the CLS token. Yeah, so I think distilled BERT has the largest sentence length of 66 in this case. And then if you pad it, then you can make it into a matrix. So if you want to do all this in one go, then you would want everything to be, kind of representing stuff like a list of variable length indices. You want to have a nice matrix, and so you can have that padded version. You can create a Tosh tensor out of it, and then just pass it as input to the model. Okay, so here we're not doing that packed padded sequence extra efficiency. We're not doing it, but yeah, and then you get the hidden vectors. So hidden vectors as in like those embeddings. Remember, one embedding per word, including a special token, and then we need to ignore all these other embeddings other than the embedding related CLS token. Okay. So that's what we want to do. So turns out the 0th index actually has that. 0th index actually has the per example per token the 768 dimensional vector. Okay, and so the 0th index, inside the 0th index, we want to just pick the first tokens representation, which is this. For example, in this illustration, is just these 3 cells. Okay, for the first sentence. Second sentence would be some 3 cells below it, and third sentence would be 3 cells below it, and so on. Okay, so again, this is just a detailed description of like how to index things, which we don't, which is not very insightful, but it's telling you how it's done. So how to index it? How to index this dimension is basically the first dimension we don't care. Second dimension we only need the 0th token basically, And then third dimension, we want everything. Okay. So this is how you'd index the data, and that's how you get the sentence embeddings for each of your sentence. Okay. Again, just like in assignment 3, it would be very prudent if you can print out and look at the shapes and get a sense of which coordinate corresponds to what. Okay, because we know that each embedding, each vector's embedding in this case is 768. So one of the numbers will be 768, and the other coordinate, one of the coordinates will be the number of examples that you want to get embeddings for, which will be 2000 or something in this illustration. But whatever the number of examples you have, that would be one of the coordinates, right? So you just need to figure out how to index them. Once you index, I mean, here we're just converting to NumPy, and you're getting basically a these features. So the number of features is 768. Now you have just a very tabular data, and you know how to process it. Okay? So any questions? So this is just a very detail of like just using a pre-trained model from Transformers library. Not all libraries are like this, but that library is very popular for hosting, I guess, many of these pre-trained models. So yeah, we'll not get into testing split and all that. Any questions about this? Yeah, so let's actually briefly discuss this, right? So here's a so here it's actually not doing that classification. So not the not the sentiment analysis, but it's actually here is an example which is slightly different model. It's not distilled BERT, okay, but it is actually distilled BERT is a distillation or whatever, some sort of smaller version of this. And we'll talk about like what is BERT base versus BERT large. They just when they build this model, they build multiple versions of it. Okay, so you can see how. The nice thing about the Transformers library is the people who built it. They have a lot of features that they have enabled, so you don't have to just rely on PyTorch. If you want, you can use TensorFlow or some other JAX and some other things. You can also have nice features, something called safe tensors and so on, which prevent malicious weights to be downloaded or getting executed on your machines. And yeah, so you can see tons of models here, but here's the, I mean, I assume you have visited Hugging Face website before. If not, it basically, this page is like the model card, and you can actually see how it works because they have an example on the page. Okay, so for example, if you want to compute, like the task being done here is basically you're masking a word and asking it to predict that word given the rest of the sentence. And so it's like a you can use it actually as a language model or fill in the blank model here, but you can actually use it as a language model. Paris is the capital of, and if you put a mask here, it'll tell you what the next word is, and then you use that word and then put a mask next to it, then you put a second word and so on, right? So this is the prediction, is the distribution over its vocabulary size. I think it's 30,000 for BERT models, so it's just producing a distribution over 30,000 things, and capital is the more I guess most obvious thing here, but it has other options also. So actually, they have a helper code right below, which is almost the same as the distill BERT. Import the model and the tokenizer, corresponding tokenizer. In fact, we probably imported the same tokenizer, and define the tokenizer in the model objects from these classes, and you're just passing calling the tokenizer first and then calling the model next. Okay, so this is like as simple as it gets for using any of these pre-trained models. Any questions about this application? So what we saw, to summarize, is just a way to use contextual embeddings instead of fast text and word-to-vec type of embeddings. Okay. We'll talk about that in a little bit more, but what we did is basically use the pre-trained transformer-based model to kind of create embeddings for some downstream task. In our case, it was just a classification task, right? So now what we'll do is briefly discuss about BERT, because now we'll kind of step out and just the context of this whole language modeling business from 2017 onwards. has been, there's been a lot of work. We'll mostly discuss the early stages, 2017, 2018, 2019. Okay. Let's do that. So BERT, we just saw a version of BERT, that is still BERT model. But BERT is not the only model, right? So actually now probably thousands of models in the same kind of not just transformer based, but also there are actually models which are also RNN based, which are somewhat competitive, not as competitive as transformer models, at least in the top of like all sorts of metrics, but they are not that bad. Okay, not that far away. So in the early days, which is 2018, 2017, there were actually multiple models which were all trying to do the same thing, which is like, train on a lot of big corpora, pre-train, and then they make the model available that you can actually use, potentially fine tune or potentially use it as the way we did it in the previous application. Okay? So here are some names: ULM Fit, Elmo, BERT, Transformer. Actually, the earlier model by OpenAI was called the OpenAI Transformer, and then they changed and evolved to other names. So here's a graph from 2019, which shows some of the some of the popular models. There are actually many other models which are not shown in this figure, but basically this model Elmo, which is basically based on RNNs, in particular LSTMs, was released in 2018 as a way to use these contextual, these embeddings, okay, as a way to create these embeddings for somebody else to use, just like Word2Vec 6 years ago. In 2012 was released, 2013 was released for other people to use these embeddings, okay. And then OpenAI released something called GPT, and Google released this BERT large and BERT base, which is what we kind of saw. Some version of it was also released. DistilBERT was released as a distillation or whatever, some sort of smaller version of that model a year later, right? So what this graph is showing is some sort of like number of parameters versus the time, and obviously this is actually not even comparable because this is 7.5 billion parameters. There's 10 billion parameters, and then GPT-3 was 175 billion parameters. So it's not even in the same scale. It's not 10 billion. So it should be somewhere like way above. But this is just showing the number of parameters for those early models in 2019. Okay. Today, actually, there's still a lot of emphasis on parameter size. Let me just show you another figure. So in this figure, I'm not showing the parameter size anymore, but just giving a sense of how many other people are also working on the same thing. Although we just discussed BERT, and maybe you're familiar with GPT chat versions or GPT-4 and so on. There are actually many models. So 2019 onwards, the previous figure ended at 2019, kind of, and this figure is continuing from 2019. Just showing you as a function of months, actually, in the first 4 months, in the next 4 months. End of 2022, beginning of 2022, end of 2022 is when ChatGPT was released, right? And GPT-4 was released, or some early version was released earlier in March, perhaps. So this is all and this is also not all the models. This is also, again, a sample of models by a few groups here. But it gives you a sense of like how many folks have been trying to build these. Doesn't have to be pre-trained models and not probably always publicly available, but nonetheless models that other people can use and build on. Okay. So let's actually come back to, and the story for all of these other models is that they're not very different from the core transformer architecture. There is obviously some adaptations that they do, but the core definition is for at least what is the transformer block was defined by the Attention is All You Need paper from 2017. So let's talk about BERT. Every model has its own story. So BERT has its story. When it was released, it was really good in terms of metrics like EM and F1. F1 score, I think people have heard of. F1 score is some combination of precision and recall. EM just means exact match. Okay, so what is this scorecard? It's just showing performance of a model, which is BERT model, on a task called question answering. Okay, so there's a data set called Stanford question answering data set. where the input is basically a question, a paragraph, and the output is a basically highlighting of which part of the paragraph is the answer to the question. Okay, so it's not like completely open-ended. It's just an input, a paragraph, or basically a text, a document, and then you're just saying, is there highlight those words or those phrase which is actually the answer to that question from that paragraph. And so BERT did really well back 5 years ago. Um, um, in multiple, I guess, versions, and not just on the squad data set. There's actually a new version, I think 2.0 for that question answer data set. But there are also other other, I guess, not data sets, but problems, multi NLI and question NLI and swag and so on. So let's not worry about what these mean. They are actually different benchmarking tasks where you can test the performance of these models. Okay. So, and this is an early model called OpenAI GPT. Now there's like multiple versions. So that's what kind of is the claim to fame for this best paper from 2019, ACL best paper from 2019. Okay. So what does like how do you categorize BERT, right? So BERT is basically a general purpose large language understanding model, or it is a language model, but language understanding model because it can also use it for embeddings and so on. You can use the model for downstream NLP tasks, and we just saw it earlier for just sentiment classification, but you can also use it for question answering. And BERT did well compared to, I guess, previous models, and we'll see one model, the LSTM-based model, for example. But also, when I say previous methods, think of word2vec, right? Word2vec was just released 6 years before this. Why not just use word2vec, and why use BERT is because of looking at data and creating contextual embeddings for the words. Okay, better representations. You get better representations. And these models, just like word2vec, you have to kind of do some sort of you have to build your own auxiliary task. Okay, so in the sense that you are basically working, your original input was just some raw data, some corpus, maybe a collection of articles, the whole, all sorts of articles on the internet, for example. So the problem is actually is unsupervised. BERT and all these models create a supervised version for themselves by saying, okay, let me predict the next word. Okay, so these types of modeling, I guess, approaches are called self-supervised learning. Okay, we have been looking at supervised learning throughout, and we'll talk about unsupervised learning next time for images, or even maybe later today. But unsupervised learning means no labels. We are still in unsupervised learning setting, but what we'll do is we'll create our own labels to make, we'll create our own task where we'll train when we don't have labels. Okay, so that's the kind of relation between unsupervised learning and self-supervised learning here. Self-supervised means I just create some labels and train myself. Okay. There's also a completely different thing called semi-supervised learning, which is think of tabular data where you have some labels for some examples and no labels for some other examples. Okay? And then maybe you can try to take advantage of the fact that you have some labels, but you also don't have labels for some other data, and build your models. Okay. Yeah. So just to this slide is talking about distinguishing this from previous models, word2vec, GLOW, FastText, and so on. Is that in general, pre-trained representations, these pre-trained embeddings, vectors can be context-free or contextual, and contextual representations can be unidirectional or bidirectional. Okay, so now we introduce like words, right? Context-free versus contextual is exactly the two categories where word2vec and GLOW would be context-free. Like it doesn't matter about the context, the embedding of the word is the same. Versus contextual, which is BERT and Elmo and even GPT 3 and 4, which will give you embeddings depending on what's the rest of the sentence in which the word is used. Okay, and the representations can be unidirectional, bidirectional. Just means what, when it's creating this contextual representation of your word, is it using the left side of the sentence or the right side of the sentence, or both sides. Okay, if you're only using one side, then you probably are unidirectional. Okay, that's just a very vague, very, I guess, very coarse kind of categorization of things. Like for example, if you just use an LSTM to get an embedding, then you are getting an embedding. Essentially, you can interpret the hidden vector to be an embedding for your word at that input, but that's only looking at the previous 3 words, previous 5 words, if it's the 5th word or 6th word, right? So that would be a unidirectional embedding. You can consider it that way. So this word is incorrect. It's self-supervised, but so the way BERT itself is trained, I don't know if we have the okay. So actually, this word here should be self-supervised. The how BERT itself is trained is actually let me just go here. Let's go here because this is a nice I mean, this is a nice description that you should look at. I think it's on the lecture goals page. If not, just search for BERT wiki page. So BERT was pre-trained on 2 tasks. Okay, depending on the task, the architecture would be different. We did this translation, and that's why we had an encoder and a decoder, and we had a specific way of ingesting input sentences and producing output sentences. Here, the task is different. So it was pre-trained simultaneously in 2 tasks. One is language modeling. So essentially like predicting the next word, but instead there's a twist. Here we are not predicting the next word. Given a sentence, we're just essentially dropping a word and saying predict that word. Okay, so instead of predicting the next word, we are just saying, okay, given a bunch of words, predict the next word. Instead of that, given a bunch of words, I dropped one of the words in my training. I know what word it is. That's why I can do cross entropy loss. Just predict that word. Okay, so and how did they create this language modeling problem is basically some given a bunch of tokens, right? Remember, we created the level of tokens are basically equivalent to words. There's no one-to-one mapping there, but given tokens, you say, okay, some tokens I don't know, I don't know what the token index is basically, and given the rest of the tokens, you're doing self-attention and all that to try to predict what that token index is basically. Okay, so basically, if you skip a token, mask a token, and you're doing the encoder forward pass, then eventually you'll get a vector representation. So eventually you'll get basically a distribution of tokens where hopefully there's a high probability mass on the token that was actually the one which is blank. Okay, so that's language modeling task. So it's almost exactly like the vanilla language modeling, except there's instead of predicting the next word, there's a different word that you're predicting. And the second example, the second type of task that it created, the self-supervised task, is called next sentence prediction. Okay, what you do is, given your corpus, let's say a bunch of sentences, and you also know that one sentence precedes the other sentence, or one sentence follows the other sentence, then you can use that information. You can pass 2 sentences as input, and if one actually is subsequent to the first one, then the label is, let's say, is next is true, and then if it's flipped, you should say is next is false. Okay, it's just a binary classification task that we constructed from our data to say whether the two sentences follow. I mean, second sentence follows the first one or not. Okay. So, for example, this sentence with some tokens, extra tokens. My dog is cute. He likes playing. For this should be, should have a high probability mass on is next, basically, or should basically say it is succeeding. The second sentence is is a reasonable sentence to follow the first sentence. Okay, that following nature is called entailment. Okay, the second sentence entails the first one. Similarly, my dog is cute. How do magnets work? There's no relation between the sentences, so you should say it's not. It's not the next sentence. Okay? So these are the 2 auxiliary tasks, basically self-supervised tasks that they created, and then they learned the weights of all the model parameters. Remember, self-attention layer, the feed-forward layer, all of them have parameters, the matrices. The key matrix, the query matrix, and there are in fact multiple attention heads there. So there are multiple copies of those matrices. So all of them were learned like using these 2 tasks. Okay. Yeah, and this is just showing how we use digital BERT. We already saw that. Okay, so I think we already discussed this. So in particular, just to give you a sense of some names, I think ResNet 18 is something that we use in the assignment 2, right? So ResNet 18 and ResNet 50 is actually the model that I guess won or second position or something in ImageNet large scale visual recognition competition 2015. VGG 16 and VGG 19 are similarly like two versions where they also won or kind of in the top 2 or top 3 of the ImageNet competition in 2014, 2015. Similarly, BERT has two versions, BERT base and BERT large. Okay, so BERT base and BERT large, the only difference is BERT base has, for example, there are a couple of differences, like BERT base has 12 encoder units. Okay, in our illustration for translation setup, we had 6 in one slide. Okay, the 6 actually was just an illustration. We didn't have to put 6 there. We could have put 2 or 1 or even 3 or something. So 12 is the choice for BERT base and 24 is choice for BERT large. Okay, so I guess this is where the depth is, right? So if there are 12 encoder units, then that means that 12 self-attention sub-layers and 12 feed-forward layers. Okay, that's a pretty deep network. And that's why you need these residual connections and layer normalization and all that extra tricks so that gradients actually flow properly and you actually learn. Okay, if you don't have these extra things, for example, batch norm, it's been incredibly hard to train networks beyond like a depth of 1, 2, or 3. Okay? And similarly, the feed-forward networks have, the BERT base, which is what I think digital BERT also kind of uses. It has 768 dimensional embeddings for each of the words. Okay, each of the tokens would have 768 dimensions, whereas the large one have a little bit more. And attention heads also 8 is what we saw in the illustration for our translation application. BERT base has 12 and BERT large has 16 multi-head attention units. Okay, that's a lot of numbers, right? 16 times those matrices at each encoder unit, and there are like 24 encoder units. There's a lot of matrices to train. Okay. Yeah, so the architecture is the same as the transformer encoder side. So in fact, there is no encoder decoder attention here. It was needed for us because we were doing translation and we had to decode it sequentially. But there is no encoder decoder attention for BERT itself, because remember the tasks were just masking a word and predicting it, and then just saying that 2 sentences, whether the second one follows the first one or not. There's no decoding specifically we're doing. Yeah, so we have already seen how we generate embeddings. CLS embedding would be the sentence representation. We used it previously. And yeah, any questions here about BERT? So we're just looking at an example model. Okay, so just because we're covering BERT doesn't mean that's like the mainstream thing. It's just an instance of the transformer canonical architecture that we're studying. Okay? There are many other transformer architectures we can look at. And so instead of looking at transformer architectures, I wanted to switch back to a different architecture around the same time that came out around the same time, but is using LSTMs. Okay, just to give you a different flavor of example architecture. With LSTMs, I don't think we looked at any popular architecture as such in terms of like a pre-trained model, because mostly LSTMs, we don't think of them as pre-trained models, but you could actually use them as pre-trained models as well. So Elmo is one example. Okay, and they were actually one of the early ones that wanted to contextualize word embeddings. Okay, so they wanted to kind of have a representation of word, which depends on the everything else in the sentence. And so basically look at the entire sentence before embedding each word, and the model itself is trained as a language model. So you guys have done language model with LSTMs already, so it's exactly the same idea, but some extra details that extra connections that they define in their model definition. So what do they do? Language modeling task, as you recall, is first of all, they had number of layers is equal to 2. So if you remember LSTM or RNN blocks in PyTorch, there is a num layers parameter. So that's not 1. Okay, so I think in your case by default it was 1, and you hopefully didn't change it. but number of layers is 2. So you are getting input. You're starting with an input embedding, maybe the word-to-vec embedding, for example, and then you're doing a 2-level. So the hidden vector output of the first level is being used as input for the second level LSTM cell. Okay, so each circle here just represents an LSTM cell, and you're doing just a language modeling. So basically, after the first 3 words, you're trying to predict the last, the 4th word, like improvisation. Let's stick to improvisation, for example. Okay, so this is just language modeling. But Elmo, I guess how is it different from previous architectures is that it also had a backward language model. So it would predict, I guess here let's stick to there's no previous word, but given a collection of words, you would try to predict the next word, and you also predict the previous word. Okay, so so you do two models, and then you would add them together. Okay, so what do you do? So what do we want here? That those 2 models you create, backward and forward language models. But now, let's say at inference time, you want to create an embedding for every word. You could take both the embeddings that you generate. So both the hidden vectors, the set of hidden vectors you generate using the forward model and the backward model, and then concatenate them and average them out. So, for example, this is the initial embedding of the word stick. Maybe the first layer hidden output was these 2, and second layer hidden output these 2 for the forward and backward. You can just concatenate them like this, and then just do some weighted averaging of them, just like the attention. Remember, attention was just doing a weighted averaging of words, vectors. Similarly, we are just doing a weighted averaging, and we get some vector for the word stick. Okay, so that's how they would get contextual embeddings. In contrast to that, so that's about LSTM model. Any question about this pre-trained model? Okay. If not, let's wrap up with one more example, which is the OpenAI transformer, which is a slightly different one than the BERT architecture. So here, so this is actually before BERT, by the way. So this is some earlier model that the group released here, which uses decoding, just a decoder for language modeling, and it makes sense. You are, you could use encoder for language modeling. You can also use decoder for language modeling because decoding is actually sequential. I mean, the encoder side, if you're using language modeling, you have to mask words like the last word or in the center word. Here, you're actually doing just vanilla language modeling. You're just trying to predict the next word. And that's why I guess these types of models are called autoregressive if you're gonna model it this way. So what you do is you kind of drop the decoder, but you keep the structure of decoding one word at a time. Okay, so you drop the encoder decoder attention. Remember, we had when we had the translation part, there was a decoder. We were doing something sequential, and we were doing some masking because obviously we get one word at a time. But we also had an encoder decoder attention because we wanted to kind of use encoder size information to kind of do the translation. Here, there's no translation. We're just trying to predict the next word. So, for example, even though we've had the full sentence, when we are trying to predict let's stick to, we would mask everything else, all the other indices. Remember, the decoder has a fixed width, can only process like 20 words or 100 words or whatever. So given the first 3 words, you mask everything else, and you're trying to predict the next word to be improvisation, for example. So basically, so if you remove the encoder decoder attention, this is actually just very similar to, it's basically the same as an encoder unit in transformer, except you're doing it one word at a time. That's called, I guess that's called OpenAI transformer. That's a pretty old model now, but just giving you a sense. I don't want to get into details. I guess since I used the word bidirectional versus unidirectional, Elmo was bidirectional, and this original model in 2017, 2018 was not bidirectional. Okay. So let's see. I think we've discussed BERT already. I will not get into details of all these representations. There's all more engineering of what to kind of surface as the embedding of a word, right? So you can concatenate, as just like with Elmo we saw, we could concatenate hidden vectors together and do some weighted averaging. Similarly for BERT also we have some details like that. Any questions about these additional details about how to use? So what we saw today so far is how to use a pre-trained model like BERT. Instead of BERT, we said digital BERT because it's much smaller. It's less than 100 MB. I think the pre-trained model. We saw that how to use it. It's pretty straightforward, just like using a forward pass in the ResNet 18 or something. And the second thing we saw is just some details about these representations, why they are a little bit different or improvement over the static representations or context-free representations from a few years ago. Okay. Any questions? Okay. If not, let's take a break for 10 minutes, and then we'll get into the next topic, just the beginning of the next topic. Okay. Before we switch topics, I just wanted to show you an example of like current work that's still trying to kind of make sense of transformers. So here's a paper from 2 days ago, or not 2 days ago, but I guess last month, which is trying to understand, like interpreting, like what is transformers, like what is the transformer unit doing? Okay, they're just trying to understand, like, okay, they're trying to bring in some geometric viewpoint of what's going on. Like for example, in particular, what does layer normalization do inside a transformer's encoder unit? Okay, and with that, they try to kind of use some example model called GPT-2 to kind of get a sense of, okay, whether the interpretation is good or not. So this is very similar to, as I said, like with CNNs, we had a half a class on just trying to understand like what's going on inside a CNN once it's trained. We just looked at weights or tensions, or at least where it's weights or activations, or where is it looking, for example, to make its classification. So here, similar effort you can do. Already self-attention tells you something about where it's attending, for example, when it's making a classification, when it's creating an embedding. But there's still ongoing effort in trying to improve the understanding of why a transformer works. Okay. Anyway, that was just we're going to switch topics now. I want to talk about what are we trying to do. I mean, I'll show you some slides for the next lecture, next deck of slides in a second. But we are trying to basically generate synthetic images. Okay, now we'll step away from text. We'll get back into images, and we'll look at a couple of techniques to essentially synthesize new images. Obviously, in this tutorial, which is on a model called what is called GAN, which we'll look at next time. Obviously, the images are not that good, right? But I think there are web sources where actually the quality of the model, the generated images is like very high quality. Okay. Obviously, the more recent iteration of these types of things is actually going from text to image. Okay, so you actually write down what you want as an from the what type of image you want to generate, and just you can generate that type of image. Okay, but here I'm just talking about if you could have some sampler or some distribution on realistic looking face images, and you sample an image. Maybe that's that may not be in the data set, but it's probably a new person's image. Okay, so we'll get there, but before that, we want to kind of orient ourselves towards images as well as a new modality, which is unsupervised learning. Okay, I mean it's new. It's not new because we just talked about self-supervised learning being basically a variation of unsupervised learning where you just create your own labels and just train. But we want to talk about unsupervised learning and then also images. Okay, so we'll split it up into 3 parts. I think today we have like about 40 minutes left. So today we'll try to just cover 2 things. What is unsupervised learning in general? A little bit of what's going on in supervised learning, and then just on autoencoders. Okay, those are the two things we'll cover. And next time we'll try to cover variational autoencoders and generative adversarial networks. Those are the two techniques to sample new images. Okay. So I didn't want to go to the lecture goals page on the syllabus on our repository, but it has, that lecture goals covers everything. But we only want to look at what is unsupervised learning, things that we already hopefully know from before. If you've done an ML course before, then you would know some of these. So that's what is captured in the first bullet point, and then we look at autoencoders. And here I'll just try to contrast it with PCA, which is something that we've heard before or worked with before. So we know what the difference between supervised learning and unsupervised learning is. Supervised learning, there are actually explicit labels. Somebody annotated these labels or created these labels. Okay, or you can call a feature column a label and just try to predict that. So you're just trying to find a mapping, some function, essentially some sort of conditional probability distribution, essentially. So given the context, given the input feature vector, we're trying to create a distribution over some output labels or maybe create a predicted target with some uncertainty. Okay. Unsupervised learning, on the other hand, involves only the inputs, only the in context, or only the feature vectors. For example, images, for example, text, it could be anything. And the goal is to learn some specific types of patterns in the data. Okay. We just want to explore and learn some patterns in the data, and we'll talk about what patterns, but there is no objective measure of success here. You're just trying to, so in some sense, categorize the data. Okay, you have some data, you have, you want to kind of compress them into, categories or segments and things like that. Okay? And so there's no objective measure of success. Whatever helps you understand data, and therefore maybe do some downstream decisions or make, maybe downstream, maybe supervised learning models. That's the only metric of whether you did well in the unsupervised learning phase. So some tasks, the tasks in black are things that we already know, and tasks in the purple are things a little bit new. We also know them, but a little bit new. So how many of you have not heard of any of these tasks in the black? Clustering, association rules, dimensionality reduction, and density estimation. How many of you have not heard of clustering or never done clustering before? Never done clustering before? You have. Okay. So clustering, so many of these things you can do with using scikit-learn. If not scikit-learn, there are other packages which also help you do that. So clustering, here is an illustration, right? So k-means clustering is basically you make some assumptions about your data. They're already numeric, maybe some vectors. You assume that Euclidean distance is a way to kind of differentiate between how these vectors are related to each other, and you just want to try to, if you specify the number of clusters, you can figure out which point is closest to which cluster. That is also, so we only specify the number of clusters, and so you discover, once you specify the number of clusters, the cluster centers correspond to these numbers. So if you say 3 clusters, then you get 3 cluster centers, and also every point's membership into one of these clusters by just being how close it is to the cluster center. Okay, so there's a blue, the red, and the green over here. These are 3 clusters. So clustering is there are 2 versions of clustering. One of the versions is when you use a generative model. Okay, so if you've heard of Gaussian mixture models, they are a generative model where they also lead to give you clusters. Okay, because you can think of a top view, like if your data set is 2-dimensional like this, then you can look at it from a top view. You can place a Gaussian here, a Gaussian here, a Gaussian here. Like if you think of a Gaussian from the top view, you have these ellipsoids basically kind of showing how the Gaussian decays spatially. And then, if you have 3 Gaussians that you fit, then essentially giving you 3 clusters. And then you would train, you would be able to generate new points which are not in the data set, but could belong to a cluster, right? So whereas if you just do k-means clustering, not like you're able to generate a new point. You can just say what is the membership of each point, but given the k-means clustering representation, which just means the cluster centers, it's not like, you can't generate a new point. I mean, you have to do something more. You have to assume something more. You can say, okay, given the cluster center, I'm going to assume some Gaussian distribution, and then again sample. That's like, that's an extra step you need to do. Okay. The reason why I want to point that out is this k-means clustering and Gaussian mixture models. The analogy between them is going to be very similar to autoencoders and variational autoencoders. Okay. You have not learned variational autoencoders yet. We're going to talk about it next lecture. But today we'll talk about autoencoders, and you'll see there's similarity between autoencoders and k-means of how they relate to a generative model, which in k-means would be something like GMM, and for autoencoders, something like variational autoencoders. The extra V variational or the V adjective in front is kind of giving it a generative capability. Okay. Also, by the way, these are NP-hard problems. So there's heuristics to, if you want to really cluster, and there's if you just write down the objective and not talk about the k-means process, which is, assigning to cluster centers, recomputing cluster means, and so on, those are computationally hard problems, at least in theory. Okay? But k-means is not solving a computationally hard problem. It's just doing some heuristic and getting you a solution. Okay. Similarly, for GMMs, if you want to fit the GMM, maximum likelihood is not enough. You have to kind of do potentially, I mean, you can do maximum likelihood, but it's just a messier problem than doing expectation maximization. Okay. So just connecting some dots. If you have heard of expectation maximization in GMMs, they're related to clustering as well. Association rules. Again, this is a very, I guess, old idea from mid 90s. Basically, trying to association rules and frequent item sets are all about just like clustering is patterns in the data, right? It's just, what are some concentrated regions in my data, and those are essentially clusters. Okay. Association rules are also similarly same thing. Actually, the frequent item sets part of it is essentially the same idea for essentially categorical data. So you're looking at what are some concentrated or high frequent co-occurrences of data values. Okay. That's what frequent item sets are, and you might have heard of algorithms like a-priori, FP growth, and those are just two of like maybe hundreds of thousands of algorithms here to mine typically typically categorical data sets, tabular data sets. It's called market-based analysis. Once you have those frequent item sets, you can actually construct what are called association rules, which are like if X, then Y, okay, type of entities. And you can also construct decision trees, decision lists also. Once you have these base rules, you can also order them and then essentially get a decision list. Okay. But that's downstream. But also the frequent item sets part is completely unsupervised. Okay. And you're not really, unlike self-supervised learning, you're not saying something is a target while doing this activity. Same thing with clustering. Next, dimensionality reduction. This is again just trying to reduce the dimensionality of your input. For example, if you have 10-dimensional input, then you want to reduce it to 3 dimensions. If you have 3-dimensional input and you reduce it to 2 dimensions here, you can do it in many ways. We have seen TSNE before. It's also a dimensional reduction technique, a nonlinear dimensional reduction technique. Here, this illustration is just showing a 3-dimensional data set. And you can see from the data set, just visualizing it, you can see that there is a plane that captures much of the variance in the data. Okay. In the sense, if you're on the plane, data is all over the place. Off the plane, the data is not spread out too much. Okay. And that plane is basically capturing much of the variance. And so that plane, if you kind of now flatten it and look at the top view, this is what you're seeing. Okay. And so that's what PCA is. And it's just a way to project data linearly down to lower dimensions and construct a new basis. Okay. And it's going to be an orthogonal basis. Okay. These principal component directions are going to be orthogonal, which means they are the inner product is 0. Okay. Those basis vectors, their inner product is 0. So that's dimensional reduction. We are going to also look at dimensional reduction today when we do autoencoders. Okay. And it's going to get us to lower dimensions potentially. But it's going to be related to PCA. I'm going to discuss that when we get there. Okay. So Yeah. So any questions about these first three, before I talk about the next three? Is a recap. So if you have not seen them before, don't worry. I mean, many of them, scikit-learn, for example, has implementations for them and examples that you can go over. But I just wanted to briefly mention, and mostly because there's going to be some connections we're going to make to autoencoders and other things. Next, density estimation. This is the more classical stats, at least from one perspective. You assume you've been given a data set and you want to say, okay, I'm going to assume a parametric distribution, let's say a Gaussian distribution, one-dimensional Gaussian. And then one-dimensional Gaussian means I have to kind of learn the mean and the variance. That's like a maximum likelihood estimation problem of what are the parameters that maximize the likelihood of the data that I've seen. And that's some optimization problem that you solve. That way you estimate the density of your that way you estimate the PDF or some PMF of your data. Okay, and I mean here just a simple one-dimensional estimation, but you could have 2 dimensions. For example, this is what I was saying that you could do if you have like a mixture of Gaussians. That is actually density estimation problem as well. Okay, so you have 2 Gaussians with some mixture weights. And then the top view looks like this, and you can see that it looks like a cluster as well, clustering output as well, right? So, and density estimation doesn't have to be also obviously on numeric quantities. You can also do it on categorical things, or point data, count data, very different types of data. It's just you need to use the appropriate parametric model here. To learn the distribution. And sometimes density estimation is hard, and that's why you might have to use EM or some other technique, including variational approximation to learn parameters. Okay, we haven't learned about variational approximation yet, but we'll see an instance next time of what is variational approximation and how does it help learn densities. Okay, so the next couple of examples are yeah, so next couple of examples are what we'll see today. One is embedding, and so we're going to do embedding in an unsupervised way. Okay, so we've been doing embeddings, creating embeddings in assignment 2 and assignment 3 also, right? So we use ResNet's fixed embeddings, for example, ResNet 18s, or in assignment 3, we had an end-node embedding where we learned or we preloaded the embeddings with Glow or one of these things. But those embeddings were trained by training some auxiliary prediction task, which means they were kind of learned via some self-supervised learning technique. Okay. We are also going to do something like self-supervised learning, but there's no explicit labels here, which is what an autoencoder, will produce also. Okay. So when we're doing dimensional reduction, the reduced dimension vector, you can then think of that as an embedding of the original thing, right? So we can actually embed images, which are also, not vectors, they're matrices, but or tensors, but we can embed them into lower dimensional, vector spaces. And so we're going to look at embedding from an unsupervised learning lens, and one of the embedding techniques we'll look at today actually is an autoencoder. And I'll comment more about this particular structure and what's going on here when we get there. Okay. So I don't want to get into the detail right here. Next thing is sampling. Okay, so sampling is an unsupervised learning task that you have at some data set. Same thing with all of these tasks, right? You have some data set, no labels. You want to somehow condense it into some object or some representation from which you can do something else, right? So here, we want to condense into some object from which we can sample new data points. Okay, obviously, if you estimate a density, once you estimate a density, you can also sample from it. For example, if you estimate a mixture of Gaussians, you can also sample from a mixture of Gaussians, right? So it's not different, but we will see how to, there'll be some new perspective on sampling. Sometimes you don't need to explicitly estimate a parametric density function and then sample. So that's going to be the new perspective here. And these are some pictures from some data set that was used. If you guys can recognize it, that's fine. If not, we can move on. So, okay, let's talk about the last two parts, right? For embedding as well as sampling, especially sampling. you would think we want to get to some sort of representation, some box, as I said, from which we can sample. So what do we want to do? We want to given some data, right? So PD, or data drawn from some distribution, PD, D for data. We have some examples, and from which we can construct some object, PM, M for model, from which we can sample points, and hopefully those points look as similar to PD, as if you got samples from PD. Okay, and there are two approaches to kind of view this. One is explicit, where you're explicitly parameterizing TM to be a mixture of Gaussians or something else, and then you learn those parameters. Or implicitly, you create a box where you're not defining any distribution. Okay, you're not defining a explicit density function, but you still getting samples. Okay, so I guess very coarsely, explicit just means you are explicitly defining some distribution, essentially, density function, and so on. Here, implicit just means that you're not explicitly defining a distribution. Okay, the opposite. So this is a slide from some tutorial by the person who kind of invented GANs. But what they want to say is, okay, there are a lot of words here, but let's just focus on, everything you have to kind of maximize the likelihood of the data at the end of the day. Okay, so we are unsupervised learning setting. We don't have targets anymore, so no cross entropy and all that stuff. Want to maximize likelihood. And the implicit way, one of the ways to do it is through GANs. Okay, so the implicit way, you're not explicitly defining what a distribution is or anything like that. Okay, so there is no probabilistic connections to be made. You're just building some gadget from which you can actually sample. Okay, whereas if you explicitly define a distribution or some collection of random variables and so on, then it's explicit, and in that there's an approximation that you can do, which is the variational approximation, and that's where variation autoencoder falls in. Okay, so there is actually an explicit density which is approximated, and that's why it's a technique to create that object which is explicit, approximation to some density function, and from which you can also sample. Okay, so when should we be okay with just doing an implicit thing, right? So if it's explicit, we know, okay, there's going to be a mixture of Gaussians, there's some means, some variances, covariances, and so on. And so when should be okay with not having all these means, covariances, or any of these statistics about a distribution, okay, any of these parameters of a distribution? The answer is just where you don't care about computing conditional probabilities, and you don't care about computing expectations, where you don't care about doing anything that you typically do with a distribution, right? So if you don't care about those things, so you just care about samples, then it's fine to do these implicit based type of approaches where you don't have to connect the gadget that you built to any distribution explicitly, as long as they are generating new samples. Okay, so here I'm just saying, if you want to simulate, basically you want to sample, and samples themselves are more useful. Like here, some samples from some object, actually again, we'll study next lecture, of some indoor scenes. Okay, so this is here, you don't really care about, when you're creating this, you also don't care about averaging out or expectations and so on of the distribution of indoor scenes or something. Okay, an example is where these are all examples where only sampling is kind of enough, and you don't care about averaging and so on. There's a task called super resolution. So the left side image is the original image, high resolution image, and let's say that high resolution image was compressed to some lower resolution image. Okay, compressed is like some averaged out, washed out. Okay, and then you want to kind of bring it back up to higher resolution. These three columns here, bicubic, SR, ResNet, and SR GAN. SR stands for super resolution. Are ways to bringing this image back to a higher resolution image. Okay, and there you don't really care about density functions anymore, as well. Density functions also. Obviously, this example here, you're not just sampling something. You are doing something like conditional sampling. So given the input coarser image, you want to increase the resolution and create a higher resolution image. Okay, so it's like a prediction type of situation. You have some context under which you want to generate. Okay, but the generation is enough. So the sampling is enough. You don't care about anything else, like inference or conditional probabilities or anything else that you generally care about when you have distributions, like filling missing data. All those things you can do if you have a distribution. Same thing, all these are conditional examples where given some input, you just want to sample some outputs that kind of feature is, that kind of, maybe have, like, even if you don't have inputs, think of like creating samples like this. You might not care about averaging and all that. Okay. Same thing with these types of, so all this I'm just showing here some conditional inputs, but given the inputs, you just care about generation, you just care about samples. Okay, mostly makes sense for more creative works, perhaps. Yeah, anyway, so I just wanted to have those couple of slides on when is implicit enough. Implicit is enough. Implicit ways of constructing an object from which you need to sample is enough if you only care about sample. That's what, I guess, the summary of those 2 or 3 slides. But anyway, coming back to what we're going to do concretely is we're going to not look at text. Although on text also you can have some generative ideas here, like this. Especially language models we've already seen. So we work with image data and we'll look at one example from each category. So on the explicit category, we'll look at variational autoencoder. On the implicit category, we'll look at a generative adversarial GAN. Sorry, generative adversarial network. Okay, or GAN for a short. In short. So both have neural networks at the core of them. In fact, if you think of images, we will have con layers or something like con layers inside. But we look at these two. These two are, I guess, the popular ways to generate images or conditionally generate images. There are also newer ways, like diffusion-based techniques, to also generate images, but we might not have time to do that. Okay, if we have time, we can consider that as well. So what do you want to do, right? So at the end of the day, both of these techniques, VAE or GAN definitions, the model definitions, and whatever the task we set up, go from training data to create this gadget. This gadget is going to be this yellow box here. Both of them create this yellow box such that given some source of randomness, which is shown on the left side, they can generate a distribution over things. Okay, in this case, a distribution over images, and so you can get a sample from this distribution. Okay, so we'll essentially build this yellow box such that given some starting randomness, we can generate random images. Okay, synthetically generated images, and hopefully they're not too far away from the true distribution of the data, which we don't know. So we don't know the true distribution of images. Okay, that's too rich, right? So it's like how many types of images there are in the world. There could be so many, right? But we will, when we train this box, we'll kind of minimize some loss with respect to the data points that we have. So these black dots are the data points that we have, our data set, completely unsupervised, and we're just trying to create this yellow box such that the distribution we learn is close to the distribution that is there. Okay? This is what maximum likelihood anyway does. Okay, so either model at the end of the day has to kind of approximate the true distribution of data. Okay, any questions here? Yeah.
So, simple words, if you're just recreating the initial image, I can understand that in the explicit case, you're kind of potentially interested in the parameters if you specify distribution, but for the implicit, like what cases would it be useful?
Wherever the images are themselves useful. So mostly creative settings, like super resolution is another example that I showed you. Those are conditional examples, so they'll need a little bit more detail. But unconditional examples, as in like we just want to generate new images. Mostly for creative settings, it makes sense. So obviously the base case is if you have a collection of images, you can always sample one of those images and call it a day. But we don't want to do that, right? We want to generate an image which looks like these images, but is not in that set, right? But yeah, you may say where is that useful? Is synthetic data creation. Okay, one of the examples. But it could be synthetic data, but you can also, it's like saying, here are the new potential images. Then you can say maybe those images kind of tell you more about the world. You learn something, but it's not you don't need to average out or anything like that, right? So it's mostly for generative purposes, creative use cases and synthetic data generation would be a couple. Um, let's actually see, because this what we're seeing is actually very essential. Just like CNNs, just like RNNs, we're only looking at the very canonical basic models. People have really stretched the limit of what we can do with these VAEs and GANs in many different settings. Okay, so and there they're actually connected to many real applications. Here I'm not done a good job of doing that, but let's actually get started with one of them. In particular, today we'll just look at autoencoder. Okay, what is an autoencoder, and why is not enough? Okay. So autoencoders, right? So before we talk about autoencoders, since we wanted to kind of specialize to images, I'm going to talk about how do we even generate images. Okay, so like what are some building blocks, right? Because we want to work with images, and then I'm going to talk about an autoencoder, which is specific to the image data. Because autoencoder for tabular data is kind of easy to describe. So we know that a neural network is a function that maps to an input and output. I mean, just like any other function. Here is an example of what we call as the transposed convolutional network. Okay, DCOM means something else in signal processing, and that's why I've striked out that word. But you can use it as long as you know that when you say DCOM, you're not talking about something else in signal processing, but this operation here. So here is a network where we're going from a vector to an image. Okay, so remember, if you want to generate an image, we have to go from some source, some starting, representation, let's say a vector, to an image. So we have to do some transformation. So for example, we can go from this vector to a tensor, to another tensor, to another tensor, and then finally a tensor which has depth of 3 and maybe a 64 cross 64 size. Okay, height and width. The question is, you may say, okay, how are you creating more numbers from less numbers, right? That's where I guess at the outset it may seem like, okay, how are you getting more numbers? It's not anything crazy, right? So there is actually there's actually a layer here, or a bunch of parameters which have probably hopefully been trained using data, and those parameters kind of lift this bunch of numbers to this higher set of numbers, higher collection of numbers. That's not hard. Actually, let me show you here, right? So we can start from a 4-dimensional vector actually and get a 16-dimensional vector. Okay, and in fact you can do it using just simple linear transformation. How do you do that? Is basically you can say, okay, in particular let's look at the left top, bottom left figure here. So let's say we have 4 numbers like this. Okay, this green 4 numbers, and we want to create. So this is 2 cross 2, and we want to create a 4 cross 4 matrix like this. Okay, so what we can do is take. So we can, and the way we can get higher set of numbers is to ensure that each number in the input side participates or produces or somehow contributes to a collection of numbers here. Okay, and that's literally a linear transformation, right? So to kind of better capture that, let's see. So if you have a 4-dimensional vector, okay, you multiply with the matrix, which is 16 cross 4. Okay, let's forget about the transpose here. That's not correct here. Then you can get a 16-dimensional vector. Okay, that's just a linear transformation. And in fact, if you think of the first coordinate of this 4-dimensional vector on the left side, you can see what all coordinates it's affecting, right? Because this first column is going to multiply with the first number of the input, right? So you can see that W00, W01, W02, 101112, and 202122 are exactly these, let's say these 9 locations here. So the first number is contributing at 9 locations, second number is contributing at 9 locations, third number is contributing at 9 locations, fourth number is contributing at 9 locations, and obviously they're getting added up, so there's some addition going on. So obviously I can go from 4 numbers to 16 numbers. That's not an issue, right? So I just need to reuse the numbers again and again. That's all, right? So this is just a very explicit way of saying you can easily go from lower collection of numbers to higher collection of numbers. Okay, so if we can go from here to here, you can imagine I can go from a smaller tensor to a bigger tensor also. Okay. In fact, the ideas of how to go from a smaller tensor to a bigger tensor will not look at in detail at all, but it's exactly very similar to striding and slicing. So striding operations that we saw with the opposite direction when we went from an input tensor to an output tensor. If we had a 3x3 filter and a stride of 1 and we had 0 padding, then we would have gotten the same size tensor at the output. Okay, but here we want bigger size tensors, and you can do that as well. Is my comment here. Yeah, so now let's talk about autoencoding, or at least some one step at a time. So autoencoding, let's talk about encoding, or at least relating two things. Okay. Firstly, if you had a vector and you wanted to relate it to an image, so I'm trying to map it back to an image setting, and the previous slide was also about images, right? So if you had a vector of all ones and you wanted to kind of, if you pass the vector of ones through a decom layer followed by decom layer and so on, like the tensor to tensor tensor, and if you want to get an image, let's say image of a cat, how do you do that, right? So that's exactly what we've been doing throughout. We know, so this is not something to be meddled with. This is a target that we already know. So we just have to tune these parameters such that given the vector of all ones, we produce an image. Okay, that's you just minimize see what current parameters, what are they producing? Is it how far is it from target? If it's too far from target, you do the gradient update so that you have new set of parameters so that the target looks like exactly what you want, right? So that's kind of easy, right? Now, let's say if you want to do it with multiple input vectors, that's also not hard, right? So let's say the vector of all ones corresponds to an image of a cat, a vector of all zeros corresponds to an image of a fox. Then you can encode, and maybe there's another vector of, let's say, all twos, which corresponds to a dog. Let's say if you have a vector and an image pair that you want to all of them to be kind of if you given that vector, you produce that image, you can learn together. Okay, you can learn the weight such that it tries to produce the first image, tries to produce the second image, given the second vector, and so on. Obviously, it may not be able to, at some point, it may not be able to reconstruct well because it has to reconstruct all these other images, but you will be able to do that. Okay, so, and that's exactly what we want to do here with one addition, which is that we also want to go from the image to these vectors as well. And that we can just use, something like a ResNet 18 type of architecture or whatever, like our CNN architecture, to go from an image to a vector. Okay, so then your full setup will look like this. You start with an image, use an encoder network or basically a convolution neural network, mostly essentially, to go to a vector of maybe a vector, basically 10-dimensional vector, 100-dimensional vector. And then from that 100-dimensional vector, you go back to the original image. Okay, and now you don't have to pre-specify what that vector is because you learn that vector, by training these parameters. So previously in the previous slide, I said, okay, vector of all ones map into a cat, vector of all twos map into a fox. You don't have to do that now. Okay, and so these things are called codes. They are called latent vectors or latent codes because you can just say it's not part of the data, and that's why it's latent. Latent just means hidden or invisible. It's not part. It's not part of the input data. Input data is just images. Okay. So this setup is what lets you learn these green things. Okay, and so you're not pre-specifying them. You can learn those green things as long as you have a bunch of images. Okay, and that's why it's called an autoencoder. Also, because you're encoding the image and then decoding some information related to the same image, and therefore you're encoding the image and decoding itself. Okay, that's why it's called an autoencoder. So what is the objective then? So what we did previously was just try to motivate, okay, we can do this. Okay, why do you want to do it? Is because what we want to do is capture some common patterns in the training data. We want to compress. Okay, we want to actually do dimensional reduction. Okay, we want to capture information in training data, and the setup that we saw is what enables it, and through creation of these embeddings of these data points. Okay? In our case, the data points are images. Bringing the data points down to these vector space is what gives us this compression or I guess dimensional reduction. Okay. generally you would keep the dimension of z smaller than x. Z is, I'm just calling the things which are vectors z's. Think of x's as the images. Then generally you would keep the dimensionality of z smaller than x's. Okay. So I've been calling them vectors clearly. So if you think of x's as images, so clearly images probably are bigger than the vectors. But you could also make the vector really long, so that the number of numbers in the vector is more than the number of pixels in the image or number of cells in the image. Okay, that doesn't make any sense, because think of an extreme case where dimension of x is the same as dimension of z. Then you can just have an identity matrix, right? You can have an identity matrix, and you can have therefore z is equal to x. And again, you have an identity matrix. You can say z is equal to again x. So you can have perfect reconstruction with just two identity matrices. Okay, you don't have to do anything. So typically, you want z to be smaller than x. And there are actually situations where you can pick z to be higher dimensional than x. Dimension of z is higher than x. But there, what you're doing is actually, again, you're doing the same thing. You want to capture some common patterns among your data set. But when you pick a high dimension for z, what you do is generally you typically add noise to x, so that you can't just do identity, and you cannot reconstruct. You cannot have low loss. Okay, when you do reconstruction. So that's called a denoising encoder, where what you're trying to learn is how to remove basically noise to learn the representation of the data. Okay. So anyway, that's a slight variation, but generally, let's think of the canonical version. Z should be lower dimensional than x. Okay. So what's the full picture then? To do this compression, remember I said the objective is to just learn some common patterns. Like if you have 1,000 cat images, they all have some common patterns. They all have ears, they all have eyes, right? That's what we want to learn through this lower dimensional vector, right? So the overall picture is that you have some input data. You have some data that's input through an encoder whose parameters you want to learn, so that you can get these lower dimensional representations, these embeddings, in a completely in completely unsupervised way, unlike our previous ways of creating embeddings. And then these embeddings, hopefully, from there you can decode and come back to the same image space, and then look at the image that you reconstructed versus the original image, how much the difference is, and if the difference is large, you tune the parameters of the encoders and decoder parts, so that you actually improve. Okay, you actually have lower reconstruction error. Okay, so this is an example of an autoencoder. In this picture, there's no relation to specifically to images, but you can imagine our previous discussion about encoders and decoders, especially decoders having this transpose convolutional layers. So you can actually go from vector to an image. Then this makes sense for images as well. Okay. So now I want to briefly mention what's the difference between this and PCA. So it's actually, if you look at this, and if you think of let's say we are in a tabular case. So x is a vector, z is a vector, x prime is also a vector. And if the encode is just a W matrix, basically a no hidden layer linear transformation, and decode is also a no hidden layer linear transformation, then this is as close as you can get to PCA. Okay, this because PCA is also just doing a linear transformation of lower dimensional space. And actually, if you explicitly draw, all the PCA is like, you have a computation step. If you look at the objective function that the PCA is minimizing, is actually very similar to the objective function that we are minimizing here. Okay, it's exactly PCA is minimizing the squared loss of reconstruction and learning this projection down to lower dimension. That's what PCA is also learning through these principal component directions and the weights and the loadings. But the difference is that here there is no restriction that the projection down to lower dimension gives you an orthogonal basis. Okay, so we are not trying to maintain an orthogonal basis when we do the projection down to lower dimension. Whereas in PCA, we are explicitly, our process is such that our minimization problem requires that your principal common directions are actually orthogonal. Okay, the inner products are 0. Okay. So this is like a relaxed version of PCA. If you do pick encoder and decoder to be just matrices, okay, or just linear transformations. So so that's the connection to PCA. Okay, so you are basically relaxing the orthogonality requirement, and we know why it's called an autoencoder. But the most important thing is that we cannot generate new samples yet, just like in PCA, just like with clustering, right? So you can, how do you generate new data points? You have to have, you need to do something more. And we'll discuss this point while we motivate the variational encoder next time. Okay. So if you want to ponder about this, just think of how, if you have a clustering using k-means, how would you generate a new point? Right? You need to have something more to the narrative to create a new point and new data point, right? So that's what's missing here. And so we'll do that next lecture. Any questions about autoencoding or autoencoders? No questions? Very clear. Okay. This is a very nice tool, especially if you're doing anomaly detection these days. There's a lot of use of autoencoders and variational autoencoders in anomaly detection. Okay, so we'll discuss this. I will continue from here next lecture.